Now let's do question 4.2. The graphs of f, which is a quadratic function, and graph of g, which is an exponential function, are sketched below. Now E and H are the x-intercepts of f. So E and H are the x-intercepts. So these are my axes right here, so that you can see them properly. And then E and H are my x-intercepts, so my graph cuts there. It also says that C is the y-intercept of f and lies on the asymptote of g. So C, which is a point here, is where my graph of f cuts the y-axis. It's a y-intercept and intersects with the asymptote of g. So this is the asymptote. Now the two graphs intersect at D, and D also is the turning point of my parabolic function. Now the first thing, write down the y-coordinate of C. Now it says that C is the y-intercept of f and lies on the asymptote of g. Now one way that we can find the y-coordinate of C is to say that it is q, because q in an exponential function is the asymptote of that particular exponential function. But in this case, we don't know what value is q, so that way it's not possible. But then again, it says C is the y-intercept of f, so we can just find the y-intercept of f. Now for y-intercept, let x be 0. So for f, I'm going to let x be 0. Therefore, I'm solving for when at f at 0. So where I see x, I'm going to substitute 0. So I'll have 0 squared minus 4 into 0 minus 5. Therefore, f at 0 is equal to minus 5. This is the y-intercept. Therefore, C here is at 0 and minus 5. Therefore, the y-coordinate of C is minus 5. That also tells us that this asymptote is equal to y equal to minus 5. So our function here of g is g at x is equal to a 2 to the power x minus 5, because g is the asymptote, and we found out that here where it intersects, it is equal to minus 5. Now let's move to 4.2.2. In 4.2.2, it says determine the coordinates of D. What did they tell us about D? They said that the two graphs intersect there, so the graphs are equal to each other there. That's one way we can find, by taking this function and saying it is equal to this one. But that would be a problem because we don't know the value of a right now. So this would be an unknown that we cannot solve for. So what other way can we do it? Now it also says D is the turning point of f, and you know that when you have a parabolic function, the x-coordinate of the turning point is equal to negative b over 2a. Now what's b and what's a? Now in a quadratic function, the function is given by f at x equal to ax squared plus bx plus c. So this is where we are going to take our a and b. Now for this function of x squared minus 4x minus 5, what is b? B is equal to minus 4. So we have minus 4 for b. Therefore, I will substitute here and say b is minus 4 over 2 into a. What is a? A here we can see is the coefficient of x squared. Therefore, it is equal to 1. So my x coordinate at the turning point there is equal to positive 4 over 2, which is 2. So the x coordinate is 2. Now what is the y-coordinate? The y-coordinate, we just take the function and substitute. We substitute the value of the x, which is 2. So we'll have 2 squared minus 4 into 2 minus 5. And that will give me negative 9. Now, that means the coordinate of D is 2 and negative 9. Therefore, D is 2 and negative 9. 4.2.3. Determine the values of A and Q. Now, we already found Q from intuition and said that Q is equal to negative 5 because it is the asymptote here that intersect with the y-intercept of F. Now, do we know A? Now, once we have Q, our G now is equal to A 2x minus 5. We have x and y that we do not know. So we need a point that can tell us what is A. We do know a point. It is D, where these two functions intersect. We know that on the function of G, we have a point 2 and negative 9. So we are going to use that here to solve for A. What is G at x? It is equal to 9. It is our y. Now we don't know A, and 2 is to the power of 2 minus 5. So we're going to take 5 into that side, and we're going to have negative 4 equal to A into 4. Divide by 4 on each side. A is equal to minus 1. So we have A and Q, meaning that our full function of G at x is given by A is minus 1. So we have negative 2x to the power 5. And that's the function of G at x. Now that we know A and we know Q, remember there's a 1 here. It's just like God. It's there, but we cannot see it. So write down the range of G. Remember that range is all the y values that your function exists in. Now when you look at G, you can tell that it starts at negative 4.2.4. Our G, it starts at y value negative 5 because it cannot pass through an asymptote. So it will be at negative 5. We do not include 5. We do not make a square bracket here. We make a curved bracket because 5 is not included in our range. And it will start at negative 5, go down, go down, go down until infinity. So negative infinity. So it starts at negative 5 and goes to negative infinity. Actually, you start from negative infinity and you end at negative 5. So you go this direction. You go from negative to positive. So it starts at negative infinity and goes all the way to the positive values. 4.2.5. Determine the values of k for which the value of f at x minus k will always be positive. Let's write that down mathematically. We are looking for values where f at x minus k will always be positive. So they will be greater than 0. What are the values of k where this is possible? Now let's take k to the other side and make it positive. We have f at x greater than positive k. You transpose it to the other side and it becomes positive. So basically we are looking where our function is greater than k. Now notice that from our function is greater than k where it exists. So our function comes all the way down until negative 9 and then goes back up. It can never go lower than minus 9. So if we make sure that our graph it's never lower than negative 9, then it can be positive. Therefore, our value of k is equal to minus 9. So wherever our function is greater than negative 9, f at x minus k will be positive.